Welcome back to The Explainer. I'm absolutely thrilled you're tuning in today because we're about to take a seriously mind-bending journey into the literal, physical infrastructure that powers the internet. We talk all the time about data, the cloud, and the massive AI boom, but how often do we actually stop to think about the physical glass strands carrying that data across the planet? Almost never, right? Well, today we're diving into a massive physical breakthrough that's completely rewriting the rules of optical communications. So how exactly do you make the internet 50% faster without actually changing the speed of light? It sounds like a trick question. I mean, if the speed of light is the absolute unbreakable speed limit of the universe, how can we possibly push our data networks to go significantly faster than they already do? It's a fascinating puzzle, and the answer doesn't involve breaking the laws of physics, it just involves completely changing the highway that the light travels on. Okay, let's dive into this. Section 1, the speed of light limit and our current technology constraints. To really get why this new tech is a game changer, we first have to talk about the limitations of what we're currently using. We usually think of light as traveling at its absolute maximum speed, around 300,000 kilometers per second. But there's a major catch. That's the speed of light in a vacuum. When you pump light through the traditional solid glass core of a standard fiber optic cable, that dense material acts as a massive roadblock. The glass physically slows the light down by about a third. So, in a world where high-frequency trading, AI supercomputing, and 5G demand literally instantaneous communication, traditional solid fiber optics are actually bottlenecking the speed of light. Which brings us to Section 2, the hollow core breakthrough. This is the massive leap forward we've been waiting for. Engineers and physicists have come up with a mind-blowing solution. To wrap your head around just how revolutionary this is, think about traditional fiber. It uses a solid glass core to trap and guide light. It works, sure, but imagine trying to run a full-speed sprint while you're waist-deep in a swimming pool. The water just drags you down, right? Hollow core fiber, on the other hand, guides the light through a microscopic tunnel of completely empty air. It uses these incredibly complex microscopic structures to keep the light confined. Moving light through an air core is like sprinting on a perfectly paved open track. The resistance is virtually gone. And the numbers back this up beautifully. Because light travels about 50% faster in air than it does in glass, the latency, the time it takes for data to travel a specific distance, drops from 4.9 microseconds per kilometer down to roughly 3.33 microseconds. That is a massive 30% reduction in latency. There's also a huge drop in chromatic dispersion, plummeting from around 17 picoseconds all the way down to less than 5. Basically, because the light isn't plowing through a dense material, the different wavelengths don't smear and spread out nearly as much. Your signal stays incredibly crisp, even over very long distances. And this brilliantly illustrates just how many cascading benefits we get here. We're talking 50% faster transmission speeds, but that's just the tip of the iceberg. Hollow core virtually eliminates what's known as the Kerr effect, a really annoying type of optical nonlinearity that distorts signals in solid glass. On top of that, we get incredibly low signal loss, and the fiber itself is highly resistant to temperature fluctuations. That last part is an absolute dream for maintaining perfect synchronization in ultra-precise networks like 5G and massive supercomputers. But get this is probably my favorite metric of the whole bunch. In a hollow core fiber, over 99% of the optical power is transmitted entirely through the air. The light barely even interacts with the actual physical material of the cable. And because of that, you can pump massively high-powered continuous wave lasers through these cables without the risk of the glass literally breaking down and melting from the high-intensity radiation. It's wild. Let's move to Section 3 and see how this builds out in reality. Splicing and testing nightmares. So while the physics are basically flawless on paper, this brilliant technology is an absolute engineering nightmare to actually deploy. We have to remember we aren't just dealing with solid, robust wires anymore. Hollow core fiber is incredibly fragile. You're essentially dealing with microscopic, highly delicate air-filled tubes. Taking these microstructures out of a pristine, heavily controlled lab and handing them over to a construction crew to drag through the mud, the dirt, and the intense pulling tension of real-world deployment, it creates immense physical hurdles. It's honestly a miracle it doesn't just turn to dust out there. The biggest headache by far is fusion slicing. Normally, when you need to connect two lengths of fiber to span a long distance, you use an electric arc to literally melt and fuse the glass together. But imagine what happens when you try that with hollow core. Step 1. The heat softens the glass. Step 2, surface tension acts on those newly softened microstructures. And Step 3, disaster. The microscopic air holes simply shrink and collapse in on themselves. That structural collapse instantly ruins the optical properties of the cable, completely bricking the connection. And the deployment complications definitely don't stop there. If you want to connect this futuristic hollow core fiber back to traditional solid core networks, you run into mode matching issues, simply because light behaves so differently in the two mediums. You also need ridiculously precise control over the splicing equipment's discharge intensity and time. I mean, even something as tiny as a microscopic burr on the cut glass, a slight tilt in the alignment, or accidentally heat shrinking the splice over a single speck of dirt will cause severe structural deformation and devastating signal loss. Then, there's the actual installation process. Because of its complex hollow geometry, hollow core fiber is up to 10 times more sensitive to bending than traditional single-mode fiber. Installers can't just snake this stuff tightly around corners or cram it willy-nilly into narrow server racks. It requires incredibly strict, large bend radii during installation. If you bend it too much, the internal structure stresses, and boom, you lose your signal. So let's say you do manage to install and splice it perfectly against all odds. How do you test it to make sure it works? Well, you're in for another uniquely frustrating surprise. Traditional fiber testing relies on measuring the light that bounces back off the glass molecules, a phenomenon called Rayleigh backscattering. But hollow core fiber is mostly air. The backscattering is 14 to 20 decibels lower. Essentially, standard testing equipment doesn't receive enough reflected light to measure the connection. The fiber practically blinds our legacy equipment. Thankfully, the industry is already stepping up to solve this testing nightmare. We're starting to see companies like VIA bringing advanced solutions to market, like the One Advisor 800, which offers specialized bidirectional OTDR and dispersion testing specifically tuned for hollow core fiber. These all-in-one certification tools are actively being tested and validated by global hyperscale data center operators as we speak, which means, despite the hurdles, this technology is finally ready for prime time. All right, let's move into our final act. Section 4, Scaling for the AI Era, and how this hits the real world. We are officially watching this tech break out of the laboratory and straight into the massive, real-world data centers that are powering this current AI boom. And there's a specific number that's really interesting right now, 350. That represents 350 feet per minute. Recently, Prysmian, Relatively Networks, and Durline teamed up to test a cutting-edge 24-fiber hollow core cable. They successfully jetted or essentially blew this cable through high-density conduits at speeds up to 350 feet per minute. That proves you don't need a lab coat and tweezers to lay this stuff. It can actually be deployed at scale using standard heavy-duty industrial installation techniques. So why does all this massive effort and investment really matter? To put it into perspective, it all comes down to 90 kilometers. Right now, data centers that need to act as one giant synchronized AI computing cluster have to be placed fairly close to each other. Because of the latency built into solid glass fiber, the absolute maximum distance between these synchronized data centers is capped at about 60 kilometers. But with the 30% latency reduction provided by hollow core fiber, that maximum distance just jumped to 90 kilometers. Operators are no longer forced to build in super crowded, expensive urban areas. They can finally build data centers further out, in regions where vast plots of land and massive amounts of power are actually available. I think Rodrigo Amezcua Correa, the CTO over at Relativity Networks, hit the nail on the head here. He said, seeing Chrono Core HCF produced and installed marks the transition from innovation to infrastructure. That perfectly captures the moment we're in. A concept that literally sounded like pure science fiction, beaming massive amounts of data through microscopic tubes of empty air, is right now becoming the physical backbone of our digital future. We have spent decades just accepting the limitations of glass. But today, the whole game has changed. With the speed of light no longer bottlenecked by a solid core, how will hollow core fiber reshape the future of global AI infrastructure? Are we just going to make our current networks faster? Or is this going to unlock entirely new distributed computing architectures that we haven't even dreamed up yet? It is an absolutely fascinating space to watch. Thank you so much for joining me on this explainer today. I really hope you leave this with a whole new perspective on the invisible light speeding just beneath your feet. See you next time.